And I understand that it's coming. Y'all hear this feedback? I'll try to get it fixed. It's not really up to me to fix it, but we'll see what we can do. Sorry for that. So if you go here, I've updated the equation sheet to include everything that you need for Chapter 5. So as you're working through Chapter 5 homework, you might just want to bring this up and look at it on your tablet or whatever, or print it out. So it has various tables. All those tables are in your book as well, but I've just sort of excerpted a few entries from all the tables. And then I've also made a change, one small change in the homework. See, that's on the syllabus. The homework for Chapter 5, I took out a question. I think it was number 16. No, for Chapter 5, I took out number 14. So here on Chapter 5, there was question number 14 there, and I just removed it. We're not going to talk about that. All right. Y'all doing okay today? Like a slim class today, huh? Thursday. Is that it? Nice weather. Okay. Well, listen, what we've been doing, so we went over temperature scales, right? There are 3 different temperature scales, Celsius, Kelvin, and Fahrenheit. You need to know how to convert between all 3 of those, and there are a couple of homework problems, and we've done questions in class for it as well. It's largely just using the equations, so just make sure that you know how to use the equations. We've also done linear expansion. That is when something expands, or when something heats up, it expands, and that has a lot of different applications. We talked about it with applications for measuring temperature. So like a mercury thermometer uses linear expansion to measure temperature. Also, we have these bimetallic strips that are used to measure temperature, like in your kitchen thermometers. Let's see, after that, what was after linear expansion? Density. Talked about density and sort of what density is. You've probably seen density, and it'll come up again in a later chapter when we do buoyancy and what have you. But density is just mass over volume. What else have we done? Andrea, what have we done? Heat, yes, so heat. Heat was a big thing. So when you have energy that flows into an object, it can increase the temperature of that object, and we worked through several problems with that. That's called calorimetry, by the way, when we do that. The Q is equal to SM delta T. You have a couple of homework problems that are related to that. Not only when temperature rises does that require thermal energy, but also when you change phases, when you go from either a solid to a liquid or a liquid to a gas. And the amount of energy required for that are called the heats of fusion or heats of vaporization. So for example, when I take a solid and I make it into a liquid, I have to put an appropriate amount of energy into that. And you find that through the heat of fusion. And then when I take a liquid and make it into a gas, then I use this heat of vaporization. That amount of energy is required to change it from a liquid to a gas. That becomes relevant, and we're going to talk about it today when we're sweating, because that's why sweating is such an effective cooling mechanism for the body, is because you have this water on your skin and it evaporates, and it carries away that heat of vaporization with it. It carries away a lot of energy from your body, which causes your body to cool. You have some homework problems related to that as well, and we worked through some in class. If you're just coming in, I have quiz 1. A few of you, quiz 1. If you weren't here last time, I handed back quiz 2. So just see me afterwards. Fix it. Let's see. Did I show you all my new me? My little guy that my little boy made for me? I didn't show you. You want to see? Yes, that's the right answer. Let's see here. This is supposed to be me. Does it look like me at all? I don't usually wear a hat, but otherwise the guy doesn't have any hair. Like Lego men are all bald. Lego women, they all have like this beautiful flowing hair, but Lego men, they're all bald. No hair for men. Yeah, I think you did a pretty good job. All right. Let's see. Where are we? As we're moving on, I'm going to probably change some of the chapters that we're going to do because there's some things that I want to get to, and so we'll probably leave some things out. But as we move chapter to chapter, I'll just make changes as we go. All right, I think we left off with that 800 grams of water as an example. Yeah, the 800 grams of water. And we decided that it would require an hour and 11 minutes. So here we're saying with this 800 grams of water and you're removing energy at a particular rate. You want to know how long it would take the water to freeze? Because to take water from a liquid to a solid, you have to remove energy from it, all right? Because that energy is causing the molecules to move around a lot, and they never actually get into this crystalline structure. All right. Now let's say if instead of here our initial temperature was 0 degrees Celsius, let's say what if T initial, I'll write with an I, what if T initial, instead of equaling 0 degrees Celsius, was 10 degrees Celsius? All right, so I have this, this water at 10 degrees Celsius, and I want to get it to be ice at 0 degrees Celsius. And so the first thing that I have to do is take out an appropriate enough amount of energy in order to do what? What do I have to do to the water before I can get it to become ice? What, Brittany? I think you just said it. What did you say? But you know the answer, right? I have to lower what? The temperature, right? I have to lower the temperature in order to get it down to the freezing point of water. That's what you said, right? Lower the temperature? No. Okay. Good. That's the right answer. So I remove energy from that water in order to lower the temperature down to 0 degrees Celsius. And then I have to remove an additional amount of energy, which is that heat of fusion. Remove the heat of fusion in order to convert that 0 degrees Celsius water to ice. You know, we usually think of if I have water at 0 degrees Celsius, I don't know about y'all, but I usually think, well, if it's at 0 degrees Celsius, then it's what? It's ice, right? Because it's at the freezing point of water. But can you think of a good example where you have water that's at 0 degrees Celsius that occurs almost every day in your life? When you have water, liquid water, at the freezing point of water. Do you think of any example of that? Every day, almost every day, probably. You encounter this. Water at 0 degrees Celsius, but it's not frozen. Okay, no, ice is frozen, right? But where do I have water that's at 0 degrees Celsius that's not frozen? No, 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 no. Because, I mean, well, clouds, yeah, they have ice and water, but that's not real. I mean, that's up in the air. Let me give you a hint. Well, welcome to McDonald's. What can I help you with? Like, oh, I want a Newton burger with cheese, blah, blah, blah. It's like, what would you like to drink with that? Oh, I'll have Dr. Pepper or whatever, or water. And then I get my cup. And I put ice in it. What is the temperature of the water and ice? It's 0 degrees Celsius, right? It's the same temperature as the ice. Otherwise, the ice would melt really quickly. So when you have water and ice together, that's water at 0 degrees Celsius, at the freezing point of water. So, you know, you could tell your friends when you go to McDonald's or whatever, you could say, gosh, this water is freezing because it's at 0 degrees Celsius or 32 degrees Fahrenheit. We just don't normally think of that water can be at 0 degrees Celsius and not frozen. And that's actually why, in order to freeze water outside, your temperature, the outside temperature, actually has to get a bit below freezing temperatures, or at least stay at freezing temperatures for a really long time, because you have to take out that extra heat of fusion energy in order to make it solid. All right, so here we have two steps. The first step is to drop the temperature from 10 degrees Celsius to 0 degrees Celsius. And we want to determine the amount of energy to do that. Well, Q is equal to Sm delta T. The specific heat of water, I pulled it up last time, but it is, it's 1, right? That's how we define a calorie. It's 1 calorie per gram degree Celsius. The mass of this water was 800 grams in the previous example. And then my change in temperature is going to be 10 degrees Celsius because I'm going from 10 to 0. So that means that I have to take out 800 times 10, that's 8,000 calories just to get it to go from 10 degrees Celsius to 0 degrees Celsius. And then the second step is to remove energy for the heat of fusion, or to remove that heat of fusion. And we did that last time. That Q is equal to M times HF. That's 800 grams. Remember, our heat of fusion is a measure of energy per mass. So that was 80 calories per gram. This is just from the previous example. That was 64,000 calories. So if I have this temperature at this water at 10 degrees Celsius, the total amount of energy that I have to take away from this to freeze the whole thing is going to be 8,000 plus 64,000, which is, what, 72,000 calories. The point being there that I have these two steps, that before I can take away this heat of fusion, that I first have to drop the temperature of the water from 10 degrees Celsius, which is above the freezing point, to 0 degrees Celsius. 2 steps. All right? And in each of those steps requires a certain amount of energy to either be input or, in this case, removed from the system. Let me try a little figure. I'm going to draw you a figure. This figure is in your book. I'm going to, sorry, can I go on from there? Are I good to go? Yeah, Kyle? No, I was just asking for the calories. But we could do it just like we did previously, right? Because it, right, whatever calories per unit time, just divide by that. Was it 50? 15, okay. There are several homework questions that are similar to this, basically identical to these for extra practice for you. Okay. All right. So if I'm thinking about water, I'm going to make a graph here. As I said, I'm pretty sure this is in your book. Let me take a look and see. Yeah, it's on page 113 in your book. So if I think about, I'm going to plot temperature here. And here, this is time. What I have here is I have a bucket of ice. All right, so I have a bucket of ice. These are ice cubes. And I want to convert that bucket of ice into a bucket of steam. All right, and so as time goes along, I'm going to heat up that bucket of ice. So I'm going to put it underneath a fire. That's my fire. Until that ice melts, turns into water, heats up to the boiling point of water, and then converts into steam. So here I have time labeled on the x-axis, but I can also, this is increasing in this direction. Since I'm adding energy to this, I can also imagine that this is my energy, that as time goes along, as I'm heating it up with this fire underneath this bucket of ice, that energy is being added to the system. All right, so initially, let's start at, say, minus 20 degrees. You know, because you can have ice that is below the freezing point of water. In fact, often you do. I'll take this up to minus 10. 0, and I'll say that this is 100 degrees Celsius. So initially my ice is going to be at minus 20 degrees, and as time goes along, it's going to increase in energy and increase in temperature as I put energy into this object, and then it's going to plateau. All right? It's going to plateau for a certain amount of time, and then it's going to start increasing in temperature again until it reaches 100 degrees Celsius, and then it's going to plateau again, and then it's going to start increasing in temperature again. Now, each of these is a particular phase or a particular stage. And each of these stages, you have different phases of matter, either liquid, gas, or solid in them. Now, in this very first stage, I only have a solid. Right? That ice is all a solid, and I'm just heating it up to the melting point of ice, or to the freezing point of water, 0 degrees Celsius. Now, in this second stage right here, what do I have in this stage? What phases of matter do I have? It's at 0 degrees Celsius, but what phases of matter do I have? I have solid, and what else? Liquid. This is like your cup of water with ice in it. Everything's at 0 degrees Celsius, but you have some ice and you have some liquid. So in that second phase, this is where I'm adding in this latent heat of fusion. I have both liquid and solid at 0 degrees Celsius. All right, water and ice at 0 degrees Celsius. Now at this point, right here, all of my ice has been converted into water. So as it increases in temperature from 0 degrees Celsius up to 100 degrees Celsius, what is the phase that I have? Solid, liquid, or gas? It's liquid, right? Right? And then at this point, I'm putting in my heat of vaporization. By the way, over here, I was putting in my heat of what? What that was called? What? It's fusion, right? My heat of fusion. Now over here, what are the phases that I have for where I'm putting in this heat of vaporization? It's at 100 degrees Celsius. So I have both what and what? I have both liquid and gas. I have water and steam. And then at some point, I put enough water into that water to convert it all to steam. So over here, I have only gas. So you see, as we add energy into these materials, we go through all these phases. And it's fairly common for us to know about water, but this is true for all things, even like metals and what have you, though the temperatures, of course, are much higher for the melting and the vaporization, of course, of metals are much, much higher than for water. Alrighty? Follow this okay? Need to know about these phases and how, as we add thermal energy into a material, what happens to it. All right. Let's look at evaporation. Evaporation is really just a fancy way of saying that we're converting from a liquid to a gas. It turns into a vapor, a vaporization. I'm sorry, evaporation. Your temperature, the temperature of a gas, or of a substance rather, a gas or a liquid, is proportional to the kinetic energy of the particles. And we said this when we started into, well, this area is called thermodynamics. Thermodynamics is really just the application of those basic concepts of energy, kinetic and potential energy, and just applying them to a microscopic scale, looking at the kinetic and potential energies of individual gas particles And so we describe the temperature, or the thermal energy of a substance, is just proportional to the kinetic energy of the substance. So if I have a gas where the particles are moving around a lot, how is the kinetic energy of that gas going to compare to the kinetic energy of a solid where the particles aren't moving at all? Is it more or less? The kinetic energy of the gas is going to be more. Those particles are moving around a lot faster. So they have more kinetic energy. They have more, a higher temperature, presumably, a higher temperature and more thermal energy. So I could write this functionally or mathematically. The temperature is proportional to the kinetic energy. And then if I plot, in thermodynamics, this is a pretty common plot, the number of particles in a gas versus the kinetic energy, it's going to look like this. Like if I have a container of gas particles that's enclosed, I have gas particles that are moving in all different directions. And some of these are going to have more kinetic energy than others, right? So like I might have a particle that's moving with a really big velocity, and so it's going to have a very big kinetic energy. So this particle right here would fall right here on this graph as having a very large kinetic energy. On the other hand, I might have another particle that's moving just a little bit. It's just sort of meandering along the path of life as it goes through this container. And so does this have a big or a small kinetic energy? Amy, is it big or small? Right, it has a very small kinetic energy. So this has a very small kinetic energy. So where would that particle, the little black particle, where would it be on this graph? Would it be to the left or to the right of the graph? Yeah, it's going to be on the left-hand side where the kinetic energies are small. So we have these subsets of particles, some of which are moving at very high speeds, like the blue particle, and then some of which are moving at very low speeds, like the black particle that I drew that has a very small kinetic energy. But most of the particles are just traveling at some average speed. And those are the particles that define the temperature, because most of our particles are traveling at this sort of average speed. But then we have some that are traveling very fast and some that are traveling very slow. Now, when we have evaporation, that means that some of the particles in a liquid are going to become a solid. Which particles are going to become, not a solid, I'm sorry, a gas? When we have evaporation, some of the particles in the liquid will become a gas. Which particles on this graph, the black, the red, or the blue, will become a gas? The blue, right. Why is it that they'll become a blue? Right, they have the most kinetic energy, that means they have the most heat. And so they have enough energy to overcome that heat of vaporization and escape this liquid and become a gas. Right, so those blue particles are the ones that are going to evaporate. Those are the highest energy particles. So the highest energy particles evaporate. And because they're the highest energy particles, they take away a lot of energy. So I'm going to write that as a parenthetical. Mainly, the highest energy particles evaporate. I'm going to write this, and they take away that energy. Their kinetic energy, because they're moving really fast, they take away that energy from the gas. All right? Now, some of the particles will actually become a solid. And in contrast to evaporation, let me go to the next slide. Let me redraw that figure. So here, on my distribution of particles, I had the high kinetic energy, I had the low kinetic energy, and then I had sort of the average particles. We said these will evaporate. If a particle sublimates, to sublimate, this occurs in your freezer a lot. We'll talk about this. To sublimate means that a gas particle or a gas becomes a solid. A gas becomes a solid. It just bypasses that whole liquid stage. In the case of this, which particles would change phase more readily to the lower state? The black, the red, or the blue? The black, because they have really low energies. And as we'll talk about freezers in just a bit. Those particles can actually sublimate and become a solid. That is, that you can have a vapor in your freezer, and it'll sublimate onto your foods and create a solid. That's called ice, right? That's what causes freezer burn. You know, freezer burn, like on a food, when you get this sublimation of gas particles onto a solid, it becomes a solid. And so these particles right here sublimate. Okay. Before we get into sweating, I know you're all excited about, we need to talk about humidity, because humidity is very important to how our body cools, the humidity. So at a given temperature, air can hold a certain amount of water vapor. And we define the relative humidity. Relative humidity is a measure of this amount of water vapor that it can hold. We call relative, it's a percentage. So like the humidity today, I don't know, I think it's pretty dry out there, right? The humidity is fairly low outside. It is low? Oh, it's cold. And usually on cold days, the humidity is pretty low. And so the humidity outside might be about 30% right now. But on a really hot summer day, your humidity around here can be 90, even 98% or so, really humid weather. All right? So relative humidity is the ratio of actual to saturation vapor density. Actual to saturation vapor density. Vapor density is just the amount of moisture that's in the air, or the amount of water that's in the air. And our relative to humidity is just going to be the actual vapor density. I'm just going to abbreviate it VD, that's vapor density, over saturated vapor density. Okay, so the actual vapor density over the saturated vapor density, and then in order to make it into a percentage, you see, it's just times 100%. There weren't any homework problems on this, and you won't have to do any calculations with it, but you do need to know what relative humidity is. Now, the actual vapor density is how much water there is in the air, and then the saturated vapor density is the total amount of water that the air can hold. Right? So actual vapor density is the amount of water in the air. And the saturated vapor density is the total amount it can hold. All right, so what happens as our relative humidity approaches 100%? This often happens in the morning time because the temperatures are changing. What happens when our relative humidity approaches 100%? Right, we get fog, right, because that water, the atmosphere, or the air can no longer hold any more water, and so it just starts going onto the surfaces around you. So that's why you get condensation on your car windows, on the grass, that you get fog often if the relative humidity is very high. All right, so this is just a percentage of the actual over the total amount that it can hold. Okay. Humidity is important to us because humidity really affects evaporation, and evaporation, we'll show in just a second, is very important to how our body cools itself. That's why often when you see temperatures, gosh, what's that temperature indicator called? The wet globe bulb thermometer. You ever heard it? WGBT? Is that what it's called, WGBT? It's like a heat index, right? And it not only measures the temperature, but it also measures the humidity, because the humidity is very important to how our bodies cool. Humidity affects evaporation. At high humidity, water condenses and evaporates at the same time. Right. So basically you have this water evaporating off of you, but you have the same water condensing back on yourself. So it's like you're not really having evaporation at all. Okay? So evaporation becomes very difficult in high humidity weather. Evaporation of water or other liquids, but water in particular. In high humidity. I like to think of it, and it's not far from the truth, but there's already a lot of water in the air, and so the water that's on your body or the water that's in a container, it can't go away in because you're already almost saturated in the atmosphere. Okay? So evaporation becomes very difficult when you have this high relative humidity. All right, so that gets us to cooling of the body. Now, one more thing, actually. This is related, but a little bit different. Self-defrosting freezers. Prevent sublimation. By keeping a very either low or high humidity. Which is it? Does a self-defrosting freezer, does it make the environment in your freezer with a very high humidity, or does it keep a very low humidity? Now remember, sublimation is when I have these water particles, or these gas vapor particles of water, that will sublimate onto an object and become ice. Which is it then? Does your self-defrosting freezer have a high humidity or a low humidity? It has a very low humidity, and they make the humidity low so that there's not many water particles in the air, and so that you don't get the sublimation onto the food items, which causes freezer burn. So while evaporation does not occur readily in a high humidity environment, sublimation does occur readily in a high humidity environment. So you need a low humidity, right? So let me write that in words. Sublimation does not readily occur in a low humidity environment. All right. That, by the way, is why it feels so nice to walk into a freezer. Like, they have those walk-in freezers, like at grocery stores and stuff. I mean, I don't know if y'all go into those, I don't. But they have these walk-in freezers to go into. And the reason they're cold, of course, so on a hot day they feel nice, but their humidity is really, really low. And so that's also a really nice thing about it. All right. So let's watch a little video. I have a video. This goes back to nutrition and what we were talking about in the previous chapter, but it also applies here. In this video, the NFL got together with the NSF, and they put together these science videos. I think we might have watched one. Is that true? The NFL videos? Yeah, so this is a similar thing, but they're talking about nutrition and then also hydration, and it sort of segues into our next topic. Let me pull it up. I think it's about 5 or 6 minutes. Sweating cools the body. You have a homework question about this, by the way. Let's say that, I don't know, this is my arm. All right, and I have a little droplet of water on my arm. That's right, it looks like a pimple, doesn't it? I have a little droplet of water on my arm, and when it evaporates, it becomes a vapor. All right, so it becomes a vapor. And the amount of energy required for it to become a vapor, Q, is equal to the mass of that droplet of water times the latent heat of vaporization. As we've been calling that H sub V. And that amount of energy is taken away. From the body. I'm going to go back. I want to show you the problem that we did earlier, because the heat of vaporization is a lot more than the energy required to raise the temperature of something, even by a fairly high temperature. So let's go back to this problem that we did. Where was it? Right here. See, so here we required 8,000 calories to change this droplet of water by 10 degrees Celsius, which is a pretty significant swing. I mean, 10 degrees Celsius is a lot more than 10 degrees Fahrenheit. So we're talking about, 20-ish or so degrees Fahrenheit. So a fairly significant swing in temperature, but it only requires about 8,000 calories. Whereas to remove that, well, this was heat of fusion, but it's a similar thing for heat of vaporization. To change phases requires a lot more energy than to change temperature in general. If you look at your latent heats, which are on that table on the website, pull it up again. So on the equation sheet, you can find the latent heats of water. See, it was 80 for that one, but look at the heat of vaporization. It's 540 calories per gram per degree Celsius. So there's an immense amount of energy that's being sucked away from your body when the water that's on the surface of your skin evaporates and becomes a vapor and becomes this vapor. It takes away that heat of vaporization. So we often find that people sweat more or less when the humidity is high. People sweat more or less when the humidity is high. Or they appear to sweat more or less. Which is it? Do they appear to sweat more or less when the humidity is high? That is, do they appear sweaty when the humidity is high, or do they appear not very sweaty when the humidity is high? More or less? They sweat more, right? Or it appears that they sweat more. That's because the water comes onto the surface of the skin, and then what happens to it? It doesn't evaporate because that humidity is really high, and so that water can't evaporate into the surrounding atmosphere. All right, so people at least appear to sweat more when the humidity is high. They still sweat when the humidity is low, and they actually do sweat less because that sweating is more effective, because when they do sweat, when the humidity is low, the sweat readily evaporates and cools the body. But that system gets disrupted when you have very high humidity, and then the sweat just won't evaporate, and so it's not as efficient at cooling your body. Do y'all know how the WGBT works, actually? This is kind of interesting. Do you know? Let me show you. So it's a wet globe bulb thermometer. So you have this thermometer, reads temperatures, and then you have this sort of like a gauze type material, I think, that is wet. And if you have a really high humidity, then the water that's on that bulb isn't going to evaporate very much, and so it'll drive that temperature reading up. Whereas if you have a very low humidity, then the water will evaporate very quickly from that wet bulb, and it'll cause the temperature to drop down for the same reason that sweating causes your temperature to fall. You're not responsible for that. I just think it's kind of interesting. That's your WDPT. You've probably seen that before. All right, let's do an example. This is an example from your book. Let me read the problem. Okay, this is example 5.6, and it talks about if you have a very high body temperature, one way to bring that body temperature down is to not use water, but to use something that evaporates much more quickly. Can you think of something that evaporates more quickly than water that you might have on hand? What is that? Rubbing alcohol, right. So rubbing alcohol has a very low heat of vaporization, so it evaporates really quickly. All right, or it's a vapor, it evaporates really quickly. That's why it feels cold, right? When you put rubbing alcohol on your body, it's because it's evaporating really quickly and taking that energy away. And so it says one method of reducing a dangerously high body temperature is to give an alcohol rub, and that evaporation occurs very quickly. It says how many grams of alcohol must be evaporated from the surface of a 70 kilogram person to reduce his temperature by 1.5 degrees Celsius. I've never had an alcohol rub. Have y'all ever had an alcohol rub? You have? Because you were, huh? Oh, okay. Was it because you were in heat exhaustion? Uh-huh. Help cool people? Was it because you were in heat exhaustion or? Okay. All right. Well, let's work this. So you have a homework problem that's very similar to this. How many grams of alcohol must be evaporated from the surface of a person to reduce his temperature by 70 kilogram person to reduce his temperature by 1.5 degrees Celsius. All right. So what we need to do here is I have this person. And we need to take energy away from that person. All right. So we need to take a certain amount of energy and take it out of that person enough to make it drop by 1.5 degrees Celsius. So I'm going to call that the Q person. And that energy is going to be taken away by the alcohol. So when you put the alcohol on his body, it'll evaporate, and it'll take away that heat, which I've called Q sub person. And so I'm going to set that equal then to the Q, the heat that is taken away by the alcohol. Now, the person isn't changing phase, right? So if we want to know the amount of heat that is required to change his temperature, it's just going to be S times M times delta T. That's our calorimetry equation. And then our alcohol is changing phase. It's going from a liquid to a solid, or excuse me, from a liquid to a vapor. And so the amount of energy that is lost by the alcohol is the mass of the alcohol times the heat of vaporization. And I want to know what is the amount of alcohol that's lost. So I'm going to solve for this variable. I'm going to divide both sides by HV. And I get an expression for M. The H's cancel. M is equal to S. This is the mass of the person times my change in temperature over the heat of vaporization for alcohol. Now, you need to know the specific heat of a person. Come away from this for just a second. If you look on your table, the equation sheet, I have the specific heat of a human is about 0.83 calories per gram per degree Celsius. Human body is mostly water, so it's close to that of water. So my specific heat of a human is 0.83, and that's in calories per gram degree Celsius. My mass is 70 kilograms, but I have to convert that into what? I have to convert it into grams. Be careful. The way to check this, often we'll be working in grams, so often in some of these problems, and you'll see this in the homework, you'll have to convert your mass in kilograms to grams. And you'll know that because my specific heat has grams in the unit. So 70 kilograms is 70,000 grams. So 70,000 grams times 1.5 degrees Celsius. And then that's divided by my heat of vaporization. For alcohol, that's not in your table, but it's in your book. It's 204 calories per gram. So alcohol has a heat of vaporization of 204 calories per gram. And then I can find that. It's 427 grams, so about 0.5 kilogram of alcohol. About 0.5 kilogram. Yeah, that's the mass of alcohol that you'll have to require. That's required in order to cool the body by that amount. It's not a very large amount, right? Just 1.5 degrees. But you still need 427 grams, which is a fairly substantial, maybe 1/2 bottle of alcohol. All right. I have another little video. This is about heat stroke and heat exhaustion. This is really just for your own interest. This was a news show that I found on YouTube. It just talks about the difference between heat exhaustion and heat stroke. We'll talk about that in a little bit, but let's just go ahead and watch it now. All right, the final part of this chapter is just on heat transfer. There are several different modes of heat transfer. We won't do any mathematical treatment. We just want to be able to identify what the three methods of heat transfer are. The first is by conduction. And this is through contact. The second is by convection. What does this require? Convection. You know, convection ovens, these were really popular for a while. I think they're still popular. What does a convection oven do? What does a convection oven do? What does it do? I'm sorry. It rapidly heats up the air, but it also moves the air around inside the oven. So convection requires the movement of the substance, like in a convection oven where it has these fans that move the air around. And that just causes for more even and more rapidly heating of the oven. So convection is by movement of a substance. This is either a liquid or a gas. All right, so like for example, in a convection oven, you have these fans and they will move the currents of air around, which will cause the heat to more evenly transfer throughout the oven. And then the third method is by radiation. This is like going out in the sun and you feel the warmth of the sun on your skin. This is by electromagnetic radiation. Or just EM for short if you want. Electromagnetic radiation, which is either absorbed or emitted. Absorbed like you in the sun. You absorb the rays from the sun, the radiation from the sun. Or emitted, like for example, you feel a hot oven in a room. Like a hot oven, if you have a oven in your kitchen, it heats up the kitchen, right? That's primarily through radiation that it heats up the kitchen because you don't really have movement of air within the room necessarily, and it's certainly not by conduction because you're not touching the oven, but it's just by radiation. That the radiation from the oven, in this case, particularly it's thermal radiation or infrared radiation, is being emitted out into the room. Now, in a particular room, you can have all sorts of different heat transfers, and you have some homework problems about this that just sort of you have to identify them. Let's say, for example, you have a room in your home. This is your room. Let's say you have a little window here. This is a window. You have all three types of heat transfer going on. Let's say it's wintertime and you have a fire. So you have logs, fire. This is in a chimney. Goes up into the air. And then here you are. So you have all different sorts of heat transfer that are going on. Let's say that you have a fan up here. What kind of heat transfer does the fan make conducive or is conducive to? Is it conduction, convection, or radiation? Convection, right. So the fan will move air, which is convection. All right. I have the fire, which is touching the surface of the floor, and that causes the floor to heat up. That would be conduction. And then I also have thermal radiation coming off of the fire and coming to your body or into the room, and this would be like radiation. All right. Similarly, we have radiation that will leave the home through the window. or it can come into the home through the window. So like if you have a really sunny room, it feels warm because the thermal radiation will come into the window. But if you have those blackout curtains that you can put over your window, what happens to the room? Is it warmer or cooler? It stays cooler if you close the curtains in the summertime. All right. All right. So you just need to be able to identify those three: conduction, radiation, and convection. Conduction requires contact between two surfaces. Radiation is just the transfer of radiation, electromagnetic radiation, and light. And then convection, which requires the movement of a substance, a liquid or a gas. I wanted to show you another video. Is that okay? This one is sort of for your own interest, but I thought it was pretty interesting. It was from one Veritasium, and it's about heat transfer and how certain materials will transfer heat in different ways. Let me look it up here.